Welcome to a crash course in Proximal Policy Optimization. Before we begin, a quick shameless plug. My Udemy courses on deep reinforcement learning, specifically Actor-critic methods and deep Q-learning, are on sale right now. Learn how to turn papers into code. Link in the description below. So Proximal Policy Optimization, or PPO for short, was created for a pretty simple reason, and that is that in actor-critic methods, oftentimes we see that the performance can fall off a cliff. The agent will be doing really well for a little while, and suddenly an update to the neural network will cause the agent to simply lose its understanding of how to play the game, and so performance tanks and never really recovers. Now, this happens because actor-critic methods are incredibly sensitive to perturbations. The reason being that small changes in the underlying parameters to our deep neural network, the weights, for instance, can cause large jumps in policy space. And so you can go from a region of policy space where performance is good to a region of policy space where performance is bad just by a small tweak to the underlying parameters of your deep neural network. PPO addresses this by limiting the updates to the policy network. It has a number of mechanisms for doing this, but the basic idea is that we're going to base the update at each step on the ratio of the new policy to the old. And we're going to constrain that ratio to be within a specific range to make sure we're not taking really huge steps in parameter space for our deep neural network. Of course, we also have to account for the goodness of state, in other words, the advantage, how valuable each state is, and the reason being, naturally, that we want the agent to select states that are highly profitable to it over time, so it wants to find the best possible states. Now, taking into account the advantage can cause the loss function to grow a little bit too large, and so we're going to be introducing a way of dealing with that by clipping the loss function and taking the lower bound with the minimum function. Something else we're going to be doing that's different than what you may be used to is that instead of keeping track of something like, say, 1,000,000 transitions and then sampling a subset of those at random, we're going to be keeping a very small fixed length trajectory of memories. And we're going to be doing multiple network updates per data sample using mini-batch stochastic gradient descent. It's worth noting that you can also use multiple parallel actors on the CPU, something like what you would do in A3C, but we're not going to deal with that in this particular tutorial. I'm just going to show you how to do the GPU implementation. So let's talk about the mini-batch gradient descent for a second. So we're going to keep track of a list of memory indices from, say, 0 to 19, and that's for the case of taking a look at 20 transitions. And let's say we want to take a batch of size 5. And so those batches could start at position 0, 5, 10, or 15. Those are the only possible positions for it to start, such that you get all the memories, you don't get any overlap, and that it all works out evenly. So what we're going to do is we're going to shuffle our memories and then take batch size chunks. So we'll start at position 0, go from 0 all the way up to 4. That is one batch. And then position 5 up to 9 is the next batch, and so on and so forth. It's relatively straightforward when you see it in code, but it's kind of difficult to explain as you're coding it. So just know that we're taking batch size chunks of shuffled memories for a mini batch stochastic gradient ascent. Other things we need to know is that we're going to be using two distinct networks for our actor and our critic instead of having a single network with shared inputs and multiple outputs. Now, you certainly can use a shared input with multiple outputs, but it complicates the loss function a little bit, and I found that performance is generally adequate with two distinct networks for simple environments. So the critic will evaluate the states that the agent encounters, and it gets the name critic because it literally criticizes the decisions that the actor makes based on which states it ends up in. So it says, hey, this particular state was valuable, we did good, or this state is stupid, we did bad, do better next time. Now this is in contrast to state and action pairs for something like, say, deep Q-learning, but it's in line with what other actor-critic methods use. And of course, the actor decides what to do based on its current state. So our network is going to output probabilities using a softmax activation, and we'll use that for a categorical distribution in PyTorch. So we'll have, in the case of the cartpole, we'll have a couple actions and some probabilities selecting each action, and then we will use the probabilities determined by our deep neural network to feed into a distribution that we can sample and use for the calculation of the log probabilities More on that momentarily. It's also worth noting that exploration is going to be taken care of for us due to the fact that we're using a distribution. So it's probabilistic and is set up so that each element has some finite probability. So even if the probability of one action goes arbitrarily close to 1, the probability of selecting the other action stays finite, so that at least some of the time it's going to get some exploration. This is in contrast to something like, say, epsilon greedy action selection and deep Q learning, where you select off optimal actions about 10% of the time. As I said earlier, our memory is going to be fixed to a length of capital T. In this case, we'll use 20 different steps. We're going to keep track of the states the agent sees, the actions it takes, rewards it receives, the terminal flags, the values of those states according to the critic network, and the log of the probability of selecting those actions. That'll become important later in our update rule. As I said, we're going to shuffle those memories and sample a batch size of 5, and we're going to perform 4 epochs of updates on each batch. Now, these parameters are chosen specifically for this particular environment, and that's one of my criticisms of PPO, is that there are a number of parameters to play with, hyperparameters. The memory length is one hyperparameter, the batch size and number of epochs, as well as learning rate, and another parameter we're going to see later, all play roles of hyperparameters in our model. And so there is a lot to tune here, but these parameters work really well for the cartpole environment, so you won't have to do any tweaking for that. Other thing to note is that this memory length, capital T, should be much less than the length of the episode. So in the case of the cartpole, the maximum episode length is 200 steps, and so 20 steps is significantly less than that, so I think it qualifies. You wouldn't want to use something that encompassed more than one episode, for instance. That would probably break the algorithm and result in poorer performance relative to using a capital T much less than the episode length. So all this is relatively simple, but what isn't so simple is the update rule for our actor. So here's where all the math comes in. So we have this quantity, loss CPI, this stands for conservative policy iteration, and it's given by the expectation value, which is just an average, of the product of the ratio of the policy under the current parameters to the policy under the old parameters multiplied by this a hat sub t. More on that in a second. And they just abbreviate that ratio as r sub t. Now, if you're not familiar with deep reinforcement learning or reinforcement learning in general, the policy is a probability distribution. That is what our actor is attempting to model, is a probability distribution, the policy. And this policy is a mapping between states and actions and probabilities. So given you're in state S sub t and you took action A sub t, what was the probability of selecting that action according to the distribution? And so in the denominator we have theta old. That is the probability of selecting action A sub t given state S sub t under the old parameters of your deep neural network. So we're going to play 20 steps, and then the agent is going to perform a learning update, and it's going to do mini batch stochastic gradient ascent. And so after computing that first batch, the parameters of the deep neural network change, right? That's how the batches work. You compute the loss with each batch and update your parameters. And so right after you've calculated that first batch of memories, the loss for that, and updated your deep neural network, the theta changes, and so the policy pi is going to change as well. And so we have to keep track of the parameters, of the probabilities of selecting each action at each time step in our memory. And then on a learning function, we're going to pass those states through our actor network, get the probabilities, the probability distribution, and find out what the probability of selecting action A sub t is, sampled from our memory according to the current values of the deep neural network. It'll be a little bit more clear in code. Just know that we have to keep track of log probs as we go along, and then we're going to be recalculating them in the learning loop. One thing we also see is that it takes into account the advantage, which is at a hat sub t. So the advantage is just a measure of the goodness of each state. We'll get to the calculation of that in a few minutes. But one thing to note is that this ratio, pi sub theta over pi sub theta old, can have an arbitrary value, right? Because you could have, let's say, pi theta being 0.99, pi theta old 0.01, and so that's a pretty large number. And in particular, if you multiply it by an advantage that is like, say, 10, 20, whatever, then that can also still be a large number. And so we have to deal with that, right? Because the whole point of this is that we want to constrain the updates to our deep neural network to be some relatively small amount. And so the way you deal with that is by adding an additional hyperparameter, epsilon, that you use to clip that ratio. So what we're going to do is we're going to clip that ratio within the range 1 minus epsilon to plus 1 plus epsilon. So let's say from 0.8 to 1.2. So that ratio is going to be constrained to be close to 1. And you're going to multiply that by the advantage. And so that'll give you some number. And then you want to take the minimum of that clipped number, the clipped ratio multiplied by the advantage, and the unclipped ratio multiplied by the advantage, take the minimum. And that is what we will use for the loss for our actor network. So this serves as a pessimistic lower bound to the loss. And they don't go into any real depth in the paper on the reasoning for this. But to my mind, and this could be wrong, I am an idiot sometimes, but my understanding is smaller loss, smaller gradient, smaller update. That's the whole point of it. So let's talk about this advantage now. So this advantage has to be calculated at each time step, and it's given by this equation. Now don't freak out, this is relatively straightforward. Once again, it tells us the benefit of the new state over the old. Well, how do we know that? We know that because it's proportional to or equal to the sum of the delta sub t, where the delta sub t is just the reward at a time step plus the difference in the estimated value of the new state and the current state. So it tells you what is the difference in the value between the next state we encounter and the current state. And of course you have the gamma in front of the v, which is the output of the critic network, because we always discount the values of the next states because we don't know the full dynamics of the environment, and so that reward is uncertain. There's always some uncertainty around state transitions. And then in the top equation, you just sum that, where you're going to be summing over gamma multiplied by lambda. So this quantity gamma is again the normal gamma 0.99 that we typically use, but this parameter lambda is a type of smoothing parameter. It helps to reduce variance, and we're going to use a value of 0.95. And for implementation, we're just going to use a couple of nested for loops. So you're going to start out at time t equals 0, and then sum from that step all the way up to capital T minus 1. So if we have 20 states, you're going to go from 0 to capital T minus 1, 0 to 18. And you have to do that because you have the v of s sub t plus 1. You don't want to try to evaluate something beyond the number of actual states that you have. That won't work out right. And so it's going to be relatively straightforward once you see it in action. And we're going to be keeping track of that gamma times lambda, which is a multiplicative constant that increases its power by 1 with each iteration of the inner loop. All that'll be made clear in the code, but fortunately the critic loss is a little bit more straightforward. So we need something called the return. So the return is just equal to the sum of the advantage and the critic value based on the memory. So whatever the agent estimated the value of a particular state to be at the time that it took it is what we're going to be using for the critic value in our return. And then the loss of the critic is just going to be the mean squared error between the return and the critic value based on the current values of the deep neural network. So once again, we're going to be passing the states through the critic network to get its estimate of values, and we're going to be also using the values from the memory as well. So relatively straightforward, even easier when you see it in code. So we have two different losses and we have to sum them, and so that'll be the sum of the clipped actor and critic. So a couple things to note here is that one, we're actually doing gradient descent, and so the coefficient of C1 for the loss of our critic is going to be positive, and the loss of our actor is going to be negative because we are doing gradient ascent and not gradient descent. We have to multiply by -1. Other thing to note is that we have this other parameter here, C2, this coefficient multiplied by S. S is an entropy term, and that only comes into play when you have a deep neural network with shared lower layers and actor and critic outputs at the top. So we don't have to worry about that in our particular implementation in this tutorial because we're doing two separate networks for the actor and the critic. And I'm going to use a coefficient of 0.5 for the loss for the critic. As I said, we're not going to be implementing the entropy term because we're doing two distinct networks. We can also use this for continuous actions. There you would use a different output for your actor network. And indeed, that's what the paper really is geared for, is for continuous action spaces. But we're going to be doing the very simple discrete case. Other thing we won't implement is the multi-core CPU implementation because that introduces even more complexity. We're just going to be using the GPU. So what do we need for this project? We're going to need a class for the replay buffer, and we're just going to use lists for this. Normally I like to use NumPy arrays, but in this case lists turn out to be a simpler implementation, so that's what we're going to go with. We're also going to need a class for our actor network and a class for the critic network. We'll need a class for our agent that's going to tie everything together. That'll have actor and critics that invoke actor and critic constructors, as well as a memory for storing the appropriate data. It'll also have functions for choosing actions, storing memories, saving models, and learning from its experiences. And in a separate file, we're going to have a main loop to train and evaluate the performance of our agent. Before we get into the coding section, I want to do a quick shout out to William Woodall. He hangs out in our Discord channel, which is also linked in the description below if you want to come hang out with some really smart people who talk about artificial intelligence, ranging from all sorts of different things every single day. Check the link in the description for the Discord. So William came to me and said, "Hey Phil, I found an implementation of PPO that I find to be in line with your general philosophy of software minimalism." And he showed it to me, and I looked at it, and it helped clarify quite a few questions I had after reading the paper. Now, the software you see here is pretty much my own code, but it was inspired by William Woodall's code, so shout out to him for helping me out on this, because the paper really isn't all that clear to me, even after reading it a few times. Other thing I want to say, and I'll talk a little bit more about this in the coding section, is that when I normally define deep neural networks, actors and critics in particular, I will use the convention of saying self.layerName equals nn.linear, self.layerName next equals nn.linear, and then I'll write the feedforward function where you use the member variables, the self.layer1 as something you can call as an object to call, and then calling activation functions within that. Now, what I found is that doesn't really work very well. In fact, I have to use nn.sequential to create the models for this, and that's one of the biggest takeaways I had from William Woodall's code, is that by using the nn.sequential, you really get this thing to work, and for whatever reason, I cannot get as good a performance using my conventional, typical way of writing these networks. Now, that I can't think of any reason why that should be the case, but it is something I've observed. I tested it, just altering that one chunk of code, how I define the models, and running it several times to take into account run-to-run variation, and it seems to be repeatable for me. So maybe, I don't know, maybe it's a configuration issue on my system. Maybe it's something I'm doing wrong elsewhere. I don't know. I don't think so. All of that out of the way, let's go ahead and get into the coding portion. All right, so let's go ahead and jump right into it with our imports. They're going to be pretty light. We'll need OS to handle file joining operations, NumPy for NumPy type stuff, and all of the torch packages. We'll need NN for our sequential model. We will need Optim, and we will also need our categorical distribution. So we'll start with our PPO memory class, and this will be pretty simple for the most part. The only input for our constructor is a batch size, and we will just implement the memory with lists. So we'll keep track of the states encountered, the log probs, I'll just call it probs for brevity, the values that our critic calculates, the actions we actually took, rewards received, and the terminal flags. So next we need our function to generate our batches. So our strategy is going to be the following. We're going to have a list of integers that correspond to the indices of our memories, and then we're going to have batch size chunks of those memories. So indices from 0 to say 4, and then 5 to 10, so on and so forth, or whatever our batch size is. We're going to shuffle up those indices and take those batch size chunks of those shuffled indices. So the first thing we need to know are the number of states. We are going to want to get our batch start list, or array, I suppose. That'll go from 0 to n states in batch size steps. Batch size. It would help if I could type our indices, and that is just the number of states in our trajectory. We're going to want to shuffle that so that we handle the stochastic part of the mini batch, stochastic gradient ascent. And then we can go ahead and take our batches using a list comprehension. So it's going to be those indices from I to I plus self.batch size for I in batch start. So it's going to take all of the possible starting points of the batches, either 0, 5, 10, etc., and go for, in the indices from that all the way up to I plus batch size. So we're going to get the whole batch from our indices. And then we're going to want to return an array for each of those. And this gets a little bit messy. And I have to be very careful not to mess up the order, because of course the order in which you return the memories definitely matters later on. We'll need rewards. And then we're also going to want to return the batches. And the reason why will become apparent later. It's because we're returning the entire array here, and we're going to want to iterate over the batches. So now we need a function to store a memory, and that'll take a state, action, probability, value, reward, and done as input. And all we're going to do is append each of those elements to the respective list. That is reward singular. And then finally we need a function to clear the memory at the end of every trajectory. And I forgot the self argument here. And mini rant here, I really don't like some aspects of Python. It took me much longer than I would care to admit to get this to run. Not because the algorithm I implemented was incorrect, but because I had a mismatch. So here I had, I believe, action, and up here it was actions, or perhaps vice versa in my original implementation. So it didn't flag as an error because it's not really an error, particularly where Python is concerned. And so it was quite a nuisance, pretty painful to track that down. Of course, if it were a more strongly typed language, then that wouldn't be an issue, but I digress. So now let's handle our actor network, and that will derive from the base nn.module class. Our initializer is going to be pretty straightforward. For our actor, we will need the number of actions, the input dims, a learning rate alpha, number of fully connected dims for the first and second fully connected layers, and a checkpoint directory. And we're also going to need to call our superconstructor, and then create our checkpoint file, checkpoint directory, and Actor-torch PPO. Now, I do it this way because I'll often do development in a single root directory, and I don't want to get models mixed up. if you have a different way, a more organized way of writing software, then you could perhaps skip this path join operation and just use a file by itself. But let's move on to the actual deep neural network. We're going to want a linear layer that takes star input dims. So we're going to unpack the input dims. So we have to pass in a list, and it's going to output FC1 dims, a ReLU activation function, another linear layer that takes FC1 dims as input and outputs FC2 dims. That gets a ReLU activation as well. Another linear layer that takes FC2 dims as input and outputs a number of actions. And then we're going to use a softmax activation along the -1 dimension. So that's the whole of our actor network. The softmax takes care of the fact that we're dealing with probabilities and they have to sum to 1. So our optimizer is going to be an atom optimizer. What are we going to optimize? The parameters with a learning rate of alpha. Of course, we need to handle the device. Which would be our GPU if possible. And then we want to send the entire network to the device. Next, we have our feed forward function, and that'll take a single state or batch of states as input. So we want to pass that state through our deep neural network and get the distribution out, and then use that to define a categorical distribution, which we are going to return. So what this is doing is it is calculating a series of probabilities that we're going to use to draw from a distribution to get our actual action. And then we can use that to get the log probabilities for the calculation of the ratio of the two probabilities in our update for our learning function. Then we have a couple of bookkeeping functions. Save checkpoint. We're going to want to say torch.save the state dictionary for our network, and we're going to save that into a checkpoint file. Then we need a load checkpoint, and that is self.load state dictionary. What are we going to load? A checkpoint file. And that's really it for the actor network. It's pretty straightforward. The critic network is also straightforward. And that also derives from nn.module. Here we don't need the number of actions because the output of the critic is single valued. It just outputs the value of a particular state, so it doesn't care how many actions there are in the action space. But it does need a learning rate alpha. It does need some dimensions, 256, and a checkpoint directory. And then we need to call the super constructor. And same deal with the checkpoint file. The checkpoint directory and critic torch. So that way we can differentiate between the actor and critic model files. And we will again use a sequential model. And so in the shout out, I was talking about William Woodall's implementation as well as something else I observed. So what I meant by the alternate method of doing a model was if you say self.fc1 and in linear, you know, if you do it that way, have fc1, fc2, the separate layers defined without the sequential model, it actually does significantly worse than if you do it with the sequential model. And I don't know why. I don't have certainly there's no theoretical reason it should do it. It must be something under the hood with the way in which PyTorch is implementing things. And it's no disrespect to the creators of PyTorch, but this is one of my biggest gripes with using these third-party libraries is you never know how they're implemented. So if something doesn't operate the way you expect, you can certainly go look it up. It's open source, but that is much easier said than done, right? You have to be familiar with not the entire code base, but a really significant portion of it to be able to make sense of a single file or a single way of doing things. So it really makes things opaque. It's an abstraction on top of an abstraction. And so, I don't know, it's part of the good, it's the bad that comes with the good for having, you know, a robust library like PyTorch. But I do it this way because it seems to work the best. And as an aside, I also can't get it to work very well in TensorFlow 2. And I suspect the reasons are related because the performance of the TensorFlow 2 is on par with the type of performance I get from doing it the other way, where you just define individual layers instead of a sequential model. So pretty interesting stuff. Maybe one day I'll get super motivated and decide to go ahead and figure it out, but I wouldn't hold my breath on that. So this is going to be a very similar model, linear layers with ReLU activations in between. The main difference is that our output layer is going to be a linear layer with no activation and a single value output. Now, of course, it handles the batch size automatically. So if you pass in a batch, you're going to get a batch of outputs as well. Again, we need our optimizer with learning rate of alpha. As an aside about the optimizer, I'm going to use the same learning rate for both the actor and the critic, and it's entirely feasible and possible, and perhaps even advisable to use separate learning rates for both the actor and the critic. At least in something like deep deterministic policy gradients, you get away with a much larger, by a factor of 3 or so, learning rate for your critic than you do the actor. Reason being, as we outlined in the lecture, the actor is much more sensitive to changes in the underlying parameters of its deep neural network. Now, ostensibly or theoretically, the PPO method should account for that and allow you to use a similar learning rate, because the actor should be less sensitive than in the case of DDPG, but I haven't tested it. So one thing you can do in your spare time is play around with differing learning rates for both the actor and the critic. Our feed forward function is pretty straightforward. You want to pass a state through your critic network and return that value. And we're going to need saving and loading checkpoints. I am just going to yank and paste those because the functions are otherwise identical. And so that is it for our two networks. Now we come to the heart of the problem, which is the agent class. Do I have an extra? Yes, I do. And this, of course, does not derive from anything. This is our base agent class. We need number of actions, a default value for gamma, which is the discount factor in the calculation of our advantages. Typically we use something like 0.99, a learning rate of 0.00, 3 by 10 to the minus 4. I got this from the paper, so if you read the paper, they do give you the hyperparameters and a little bit of detail around the networks they used, but it is not a very well written paper. It's rather obtuse, so I'm not a huge fan of it. But we do have some good default values from it. So policy clip. So in my cheat sheet here, I have a value of 0.1 as a default. Although in the paper they use 0.2, perhaps I was experimenting. I will have to be careful with that. A batch size of 64, a default N of 2048. So that is the horizon, the number of steps before we perform an update, and a default for the number of epochs. Now these parameters come from the values for continuous environments. So the actual numbers we're going to be using are going to be significantly smaller. As I said, we'll use an N of 20, 3 epochs, batch size of 5 instead of 64. And I'm going to go ahead and set that policy clip to 0.2. Now that I'm looking at it, we need a GAE lambda. That is the lambda parameter, but of course you can't use lambda because that is a reserved word for Python. What else do we need? Yeah, I think I'm missing something in my other file here. That's okay, I'll fix it on the fly. So then we go ahead and save our parameters. Number of epochs, and our GA lambda. We need our actor network. Input dims and learning rate. Takes input dims and alpha. PPO memory, batch size input. 1 second. All right, hopefully that is not as loud now. The toddler is playing with his grandparents, always a hoot. So now we need a function that handles the interface between the agent and its memory. And it's just going to be very simple: self memory, store memory. It's just an interface function. Then we need a function to save our models. Print saving models. That is just going to be an interface function between the agent and the save checkpoint functions for the underlying deep neural networks. And very similar for the load models function. Now we have a visitor. All right, that is it for our bookkeeping functions. Next, we need something to handle choosing an action. That'll take an observation of the current state of the environment as input, and we want to convert that NumPy array to a torch tensor, and we're going to add a batch dimension because the deep neural network expects a batch dimension, and we'll be sure to specify that it is a float. And then we're going to go ahead and pass that through our neural networks. So dist equals self.actor state. That'll give us our distribution for choosing an action. We need the value of that particular state. And then to get our action, we just sample our distribution. And then what we want to do is go ahead and squeeze to get rid of those batch dimensions. And this might be something I added for TensorFlow too. I don't remember if Torch requires it, but it doesn't hurt anything. So for the probs, we want to go ahead and return the log probability of the action we actually took dot item. So dot item will give you an integer, and likewise for the action, we want to squeeze it and get the action, the item out. And similarly for the value. And then just return all three. So this will make our main function look a little bit different than we're used to, because we're going to be accepting 3 values from our choosAction function instead of 1. But that's necessary for keeping track of the probabilities and values as well. Next, we come to the meat of the problem, so to speak, our learning function. So we want to iterate over the number of epochs. So we're going to have, in this case, 3 epochs. At the top of every epoch, we want to get our arrays, the old probabilities, the values, the reward, the dones, and the batches. Let's do that. And then I'm just going to use a different notation here and go ahead and start calculating our advantages. So our advantage is just going to be a NumPy array of zeros, len reward, type MP float 32. And we're going to say for t in range, so for each time step, len a reward array -1, because we don't want to overwrite the, or go beyond the bounds of our array. Our discount factor is going to be 1. The advantage at each time step starts out as 0. So for k in range, so we're going to start out at t and go from t to the same reward array -1, and say a sub t plus equals discount, so that GAE times lambda factor, which starts out as 1, times, we need parentheses, reward array sub k plus self.gamma times values k plus 1 times 1 minus int done array k minus values sub k. And then we say discount times equals self.gamma times GAE lambda. And at the end of every calculation, at the end of every k steps, advantage sub t equals at a sub t. And at the end, we're going to turn advantage to a tensor. In particular, a CUDA tensor. And this is just a strict implementation of the equation from the paper. So this right here in parentheses is the delta sub t. So it's a reward plus gamma times v sub t plus 1 minus v sub t, or, you know, we swap the k and t here. And you need the 1 minus dones on the values as a multiplicative factor of the values of t sub t plus 1, because the value of the terminal state is identically 0. That's just a convention in reinforcement learning. It predates the deep neural network stuff. It's just how we handle it. It's assumed. That's why they don't put it in the calculation. It is assumed. It's just a matter of convention. And then that discount is the GAE, the lambda multiplied by the gamma. That takes care of the multiplicative factor. So it is the gamma lambda to the t minus 1 power, or is it t minus k minus 1, something like that power, multiplied by the delta, and then you're summing it all up. So now we have our advantage. I'm going to convert the values to a tensor as well, and I fully admit here that going from val's array to, you know what, in fact, let's do this. No, let's leave it the way it is. May not be the most effective, or excuse me, the most efficient way of doing it, but sometimes I just get stuff to work and then don't go back and clean it up. If you want to clean it up, please do so. I always invite that. And it looks like I'm missing something here because it is not automatically indenting, so I'm probably missing a parenthesis somewhere, and it is right here, I believe, if I am not mistaken. Yeah, there it goes. All right, so then states is just going to be a tensor state array sub batch d type t.float to self.actor.device. And we're kind of violating the PEP8 style guide by going beyond 80 characters, but I think we'll be all right. Old probabilities gets converted to a tensor. And I don't need an explicit D type there, I don't think. Dot device dot to self.actor device, that works. And then actions. Okay, and then so we have the states we encountered, the old probabilities according to our old actor parameters, the actions we actually took. The next parameter we need, so we have the bottom of that numerator, pi theta old, we need pi theta new. So we have to take the states that we encountered and pass them through the actor network and get a new distribution to calculate that those new probabilities. And we'll also need the value of the new values of the states according to the updated values of the critic network. So we may as well get those now. And we can squeeze those. And then we can calculate our new probabilities. And take the prob ratio. So here I'm going to exponentiate the log probs to get the probabilities and take the ratio. You could also do this. Those two are equivalent by the properties of exponentials, excuse me. And then we're going to calculate our weighted probabilities and, sorry, our probability ratio. The weighted probabilities. I think I have two lines that do the same thing in there. That's funny. And that's going to be the advantage batch times the probability ratio. Then we need the weighted clipped probabilities. And that is going to be the clamp of the prob ratio between 1 minus self.policy clip and 1 plus self.policy clip multiplied by advantage sub batch. Now our actor loss is going to be the negative minimum of the weighted probs or the weighted clipped probs dot mean. And our returns for our critic loss are going to be the advantage plus the values for that particular batch. And so our critic loss then is going to be the returns minus critic value squared and the mean value. Our total loss, actor loss plus 0.5 times critic loss. Remember, we're doing gradient ascent, and there's a negative sign in front of the actor. So we're not doing descent. That's another thing that's kind of suboptimal about the way the paper is written. You can get kind of confused about negative signs if you're not paying very careful attention. Next, we have to zero our gradients. I think you can probably hear that my son is giving a concert downstairs. He's playing the drums by whacking on his toy box with some drumsticks. So we're going to back propagate our total loss and then step our optimizers. And finally, at the end of every epoch, yeah, I think that's the right indentation, we want to clear our memory. So at the end of all, at the end of all the epochs, we want to clear our memory. Let me just make sure I'm not doing that each epoch. No, I am not. Okay, that is good. So now let's do a right quit, and I have an indentation error here. I see. Oh, that came in when I did the yank and paste. All right, so that is it for our agent file. Let's go ahead and take a look at main. So we start with our imports. We'll need gym. We'll need numpy to keep track of the running average of our scores. From PPO torch, we'll need our agent. And if you're new here, I have a utility file that I use a matplotlib pyplot function to plot the running average of the previous 100 games for the learning curve. It's pretty trivial. You can just do a plot of the running average. Just do a git clone if you want to use my exact version. I don't go over it in every video because it's kind of redundant, but I leave a link in the description to the GitHub, so go ahead and do a clone of that so you have that file, or just write your own. So we're going to use the very basic cartpole v0. Reason being, we don't need to spend a whole lot of time on a very computationally complex environment to realize we made a mistake. So it's very easy to see if something got screwed up with the cartpole environment. This certainly will work on more advanced environments, but it does require a little bit of fine tuning. So we'll just start with the cartpole, and then you can play around with other environments at your leisure. So we'll use the parameters I dictated in the lecture. I think I changed the number of epochs to 4, learning rate of 3. We can get the number of actions directly from our environment. Very handy. Pass in all the other relevant parameters. Get the number of input dimensions from our environment. And we're only going to play 300 games. As I'm looking at this, I do realize that in the parameters I did the last time I ran it, I did do a policy clip of 0.1. But 0.2 comes from the paper, and I'm pretty sure it works both ways, so we will find out. If we need to, we can go back and change the policy clip. Not a big deal. So plot/cartpole.png. We need to keep track of our best score. This is a minimum score for the environment. An empty list for our score history. And number of learn times we call the learn function. You can make this a member variable of your agent if you want. And an average score starting out of 0. We don't actually need that, but whatever. So we'll say at the top of every episode, I want to reset our environment, set the terminal flag to false, and a cumulative score to 0. While we're not done, we need to choose an action based on the current state of the environment. Get the new state, reward done, and debug info back from the environment. Increment our score by the reward, and store that transition in the agent's memory. Reward and done. And if n, I do need an extra variable here. We'll say n steps equals 0, and that's the number of steps we've taken. We need that because we have to know how often or when it's time to perform the learning function. So every time we take an action, the number of steps goes up by 1. So if n steps modulus n equals 0, then agent.learn iters plus equals 1. And then no matter what happens, we want to set the current state to the new state of the environment. And the end of every episode, append our score and calculate our mean. And that's the previous 100 games. If that average score is better than the best known score, then set that best score to the current average and save your models. And we also want some debug information. Is sod I score of course that should be an average score. The I like to print out, this isn't necessary, but the number of steps that have transpired in total and the number of times the agent has called the learning function. This gives you an idea. I did this because when I compare with the results of the paper, it wasn't clear to me if they were talking about the number of times they called the learning function or the actual absolute number of time steps in the environment. So I print out both. These time steps and learning steps are totally optional. You don't have to print it out. It's not something that is required. So I just do it for my own clarification. We need an x-axis for our plot, len score history, and plot learning. Oh, certainly. Let's do this. We don't want to do it every single game. We want to do it at the end of all games. All right. Now, moment of truth. Let's see how many typos I made. So it's telling me init got an unexpected argument, input dims. That's interesting. What do I call it? I don't have it there. Oh. And the reason is my computer had a hard lockup and I had to do a reboot. And it mutilated my cheat sheet for this. So there's bound to be some errors in here. I didn't do my make directories. So temp, PPO, and plots. Let's try it again. Name Duns array is not defined. It's probably done array. That is in line 161. So it is Duns array. Yeah. We'll just change it there, I guess. Old prob array is not defined. That's probably the same thing. Where am I? Yeah, old prob array. And I'll do the opposite here. I'll make it singular just for the sake of not being consistent. Index 8 is out of bounds. Okay, so then something has gone extremely wonky with the generation of the batches. Okay, let's take a look at that. Oh wait, let's read this a little bit more carefully. It says index 8 is out of bounds for axis 0 with size 0. So our action array, oh, you know what? Let's take a look at our memory. So it's action array. So here we have self.actions. We return the self actions. There we go. That's why. So actions.append action. All right, now let's try it. Name advantage is not defined. That is a typo. That is in line 183. A advantage. Yeah, let's try that. Let's try once more. Has no memory underscore clear memory. That's memory dot clear memory 197. All right, so now it is running. So I'll let that go for a few minutes and we will see how it does. All right, so it has been running for a little bit, just a few minutes now. It runs relatively quickly. And what I'm seeing is that we do get some oscillations in performance. You see it'll hit 200 for, several games in a row. And then it'll drop down into the mid 100s, even, 66, something relatively low like that. And there's a little chunk here where it dips below 100 points. So It's not a silver bullet, but it looks to be recovering. So we'll give it another 80 runs and see how it does. Okay, so it has finished up, and you can see that it finished strong with a long run of about 50 games, 45 games of a score of 200. So I commented when I was writing the agent that I was looking at my cheat sheet and had a policy clip value of 0.1. It could be that I had settled on that value based on some experimentation, and then changed it back just to be more consistent with the paper for this particular video. So that's something I would play with. Other thing to consider is that there is significant run-to-run variation. That is a facet of pretty much every algorithm in deep reinforcement learning. It just has to do with the way the neural networks are initialized, as well as how the random number generators initialize the environment. So when you see papers, they'll typically report average values for, say, 5 or 10 or whatever number of games, and then a band to show the range of variance for run-to-run variation. But this is clear evidence of learning, it achieves a score of 200 in under 300 games. So I call this good. To me, this is fully functional. Now, there are a number of things you can do to improve on this. You can get it to work with continuous environments. You can bolt on some stuff for doing Atari games, where you would need to add in convolutional neural networks as your input layers and then flatten them out to pass them to a linear layer for the actor and the critic. And you can see my earlier video on an AI learns to beat Pong for Q-learning. There I go over all of the a lot of the stuff you need to do to modify the OpenAI Gem Atari environment to do frame repeating. That's something they do in Q-learning. That's an exercise to the reader. Actually, I don't know, thinking back to the paper, I don't recall if they actually do any frame repeating or not in this particular algorithm PPO, but it's just something to look at anyway. So there's a number of things you can do to improve upon it. I haven't added this module to my course yet. I'm still working on it. I really want to take some time to give more thought to the paper, because the paper isn't very well written, and I'll probably have to do a lecture like what I did for this YouTube video in the course, because the paper isn't very easy to implement just by reading it. So I hope that was helpful. That is PPO in just a few hundred lines, full implementation in PyTorch, solving the cartpole environment. Then you can easily modify this to do other environments as you wish. If you've made it this far, please consider subscribing, hit the bell icon, leave a like, a comment down below, and I'll see you in the next video.